Hello and thank you for joining me today on this video. I was thinking to make a short presentation about a sensor fusion algorithm implementation for attitude estimation. So behind this implementation we have a paper called a new orthogonalization and sensor fusion algorithm for attitude estimation, which describes in more details the approach behind the code. Okay, so if we scroll down, we will see here that we have presented the main steps, which are described very shortly here. Okay, we have the integration, then we have to modify the rotation matrix. Okay, then we have to correct the correction part. Anyway, if you want to understand more about this and about this approach, please feel free to read this paper. I will provide a link into this description, okay, to see and understand better what we are trying to do here and how we try to make the data fusion. Okay, so this approach could be used in many applications, but for today's example, we have choose to work with an IMU, which is an gyroscope and accelerometer. Okay, um, so I will now just close this and open this. Well, the focus for today is not to explain the logic behind the algorithm. I will just make a short presentation how to integrate this, let's say, library in your application, and maybe it will fit your need. Okay, so um, we have here a file called gendigits.c and .h. So this is all that you need. Okay, these two files. Okay, so this could be used as an alternative to the Madwick filter or to Kalman for sensor fusion data. Okay, so the function is called general digits fuse IMU sensor, which has as input the data from accelerometer on X, Y, and Z axis and from gyroscope. Okay, so as you can read in the description, the linear acceleration for this axis is in this unit, and then the angular rotation, okay, it's in this unit. Then the output will be the Euler angles X, Y, and Z, and a short conversion to the quaternions also for displaying the object on the screen. Okay, so the configuration which are provided here are this. So you have the sample time here. In my case, is I have a task which runs at 10 milliseconds, and then you can also increase or decrease this factor k. Okay, this library also provides well, it's the first release of this algorithm, so maybe some additional improvements in the future. So you can also configure this filter, a low pass filter here, so you can apply a filter on the output if you want. You have this basic filter here. Okay, so let's start with a real example. So let's say that you integrated this into your framework. Then you have a task which runs at I don't know, 5 milliseconds, 10 milliseconds, 20 milliseconds. This depends on your application. But the whole thing that you need to do is to in your main file where you want to call our function is to define um, these variables as external, okay, because these ones are the output, okay, provided by the library, okay. So you have the quaternions and the the three axes, okay, the angles for each axis. Okay, so this is it here. Then you need to in my case let's just ignore this. Okay, you need to read the data from the MPU in my case. Okay, so just a short overview. Here I'm reading the data through the I2C protocol from the MPU, okay, and return this as a structure. Okay, so you must define a structure like this. Okay, so you can choose this how you want to customize your code. And then I'm also providing, if I want here, a moving average on the raw data, but this is not mandatory. I just can remove this. I just wanted to, it is here, but you can ignore it also. I just didn't want to delete it. Okay, then I have here the conversions. Okay, so the raw data is somehow here I have some offsets. So you may need to calibrate. So I just made a very um, not very good calibration here, but you need to do this also. And then after subtraction or the offsets, maybe you need to convert this to the correct unit which our library is expecting, as mentioned in the description. Yeah, here. Okay, then this is needs to be done for accelerometer and for gyroscope. Okay, then you only need to call, okay, the function. Okay, this is it. Okay, so you only need to call the function with the raw data converted in the corresponding units, and the library will know to store the output into the these variables here. Okay, so then what I'm doing here just for testing is I will just print these to via Word. Okay, just to see what is the behavior of my let's say in my case my quadcopter. Okay, so let's make a short test for this library. So let's check if the filter is okay. So if you press here 1, then your filter will not have any impact. Okay, yeah, it's just a simple low pass filter. Okay, then yeah, I think we are good to go. So I will just now program the target. Okay, so I have here a hardware. It's basically my quadcopter placed on on some uh, just one axis I want to check today. Okay, so I also have this. So before testing, let's see a little bit what happens. So as you can see here on the left corner, we have um, the accelerometer data. So now it is horizontal, which is you see on the z-axis we have 10, the value. Then we have almost 0. Okay, we have some offsets here, but let's just ignore it a little bit. It is a problem because we don't have the magnetometer included, so we have a small drift on the z-axis, but it's perfectly normal. There is no problem. Maybe in the future we will also add this to the algorithm. Okay, when we'll use another MPU. Okay, so let's now just a little. Okay, I will just put here the axis. Okay, so I will now move this just to see the behavior. Okay, good. Now let's try another angle. Okay, it's a little bit. Now the rotation. Okay, so yeah, it works. Now, yeah, it's perfectly normal if I just shake it a little bit. It will maybe not behave so good, but let me try. I will just shake it a little bit. You will see this when you will start the motors. You will see that maybe you will have the same behavior here. So a fine tuning may be needed to have this working. Okay, so this means that the raw data must be somehow filtered a little bit. So yeah, um, in order this to work on the real when the motors are on. Okay, now let's just let's say make use of the our filter maybe to change the behavior of this system. Okay, so now if I'm just shake it, okay, so it doesn't like this. Okay, I will now introduce the filter. Maybe this will be needed in the future for sure. So you only need to go to the C file and let's change it to 0.02 maybe. Let's exaggerate a little bit and make it like so. Okay, let's program this. Now we should see a very big delay, okay, between my movement of the axis and the behavior, okay, on the screen here. Okay, let me just place this one. Okay, so now I will just make a fast. Okay, so as you can see, we have a big delay here. Okay, this is due to the filter. Okay, so you can play with this if you want to make use and fine tune for your needs. Okay, so I will provide a link in the description to this library, and please, if you have an application, if you want to make give it a try, please do it and provide me a feedback. So in order to maybe correct something if it's needed or to make it better. Okay, so thank you and have a nice day. Bye.